Hello students, welcome to the next class of topology. In this section, I would like to prove that the property connectedness is also preserved under continuous map. So we already discussed about what are the properties or when will a property is said to be preserved under continuity. So suppose we have two topological spaces x and y, and suppose that x is a connected topological space, connected, okay, and if there is a map f from x to y, this map is onto and this is continuous. Suppose that it is continuous, then you consider f of x. What is f of x? Since the map is onto, f of x is y itself. When it is not onto, f of x will be a subset of y. Okay, when x is connected, we can prove that the continuous image of connected set x is also connected. Okay, that means we can prove that when x is connected, f of x is connected. Here, since f is onto, f of x is nothing but y, therefore we prove y is connected. That means y is continuous image of connected set, therefore it is connected. So I can say that connectedness is a property which is preserved under continuity. So connectedness is a property which is preserved under continuity. Or in other way I can say that continuous image of connected set is connected. This theorem is also restated as continuous image of connected space is connected, or connected set is connected. Okay. This theorem can be restated as connectedness is a property which is preserved under continuity, or continuous image of connected space is connected. Or in another way, let f from x to y be continuous surjection. Then if f is connected, so is y. If x is connected, then y is also connected. This is we need to prove. Okay. Okay. So let f from x to y be continuous surjection. Since it is surjective, f of x is nothing but y. Okay. If x is connected, I assume x is connected. We have to prove that y is connected. So I assume if y is not connected, what will happen? Assume y is not connected. If you assume y is not connected, then by definition, I can write there exists two non-empty open sets A and B such that y can be written A union B and A intersection B equal to empty. That means y has a separation. Y can be split into two sets such a way that they are non-empty disjoint. Okay. Now, y equal to A union B means, suppose this is our y, then y is nothing but A union B, and you can see that A is disjoint also. So it has no common elements. So I consider, suppose this is A and this is B. So we assume that y is not connected. Therefore, y can be split into two sets A and B, which are non-empty sets, and they are open sets. Okay. By the equivalent conditions of connectedness, I can assume such open sets. I can take such open sets. Okay. Now, A and B are subsets of y, right? Since A and B are subsets of y and f is an onto map corresponding to every element here, they will have a pre-image. So, corresponding to every element in A and every element in B, there are some elements which are mapped into elements of A and B, right? So, using that ontoness, and the map is continuous also, and we have assumed that A and B are open sets, right? Therefore, by continuity, inverse image of open sets will be open. So f inverse of A will be here and f inverse of B will be here, which are some open sets in capital X. because f is continuous. Okay, since a comma b are open in y and f is continuous, right? F is continuous implies f inverse of a and f inverse of b are open in X, because inverse image of open set is open because f is continuous. Okay, and you can see that since A is non-empty and B is non-empty, their inverse image is also non-empty. Since A comma B is non-empty, f inverse of A and f inverse of B are non-empty subsets in capital X. Ready? Now what is x? Since f is onto, x is, I can write actually f of x is nothing but y. Since f is onto. Since f is onto, f of x is nothing but y itself. Okay. Then I can write x is equal to f inverse of y. Okay. That is x is equal to f inverse of, what is y? Since y is not, by your assumption, y is not connected means y equal to a union b. So y can be written a union b. So x is equal to f inverse of a union f inverse of b. Okay. So what you get now? When you choose y equal to some a union b, a and b are non-empty disjoint open sets, then f inverse of a and f inverse of b are non-empty disjoint open sets. Can you prove the disjointness of f inverse of a and f inverse of b? If f inverse of a intersection f inverse of b is non-empty, suppose you assume their intersection is non-empty, then you can consider some elements, some x belongs to f inverse of a intersection f inverse of b. So which means x belongs to f inverse of a and x belongs to f inverse of b. Okay, which implies f of x belongs to a and f of x belongs to b, right? Which means f of x is an element belongs to both a and b. Therefore that belongs to a intersection b. Is it possible? No, because a intersection b is taken as empty because they are in disjoint sets. Since they are disjoint, it is not possible. Therefore f inverse of a intersection f inverse of b is always empty. So I can say that, which implies f inverse of a and f inverse of b are two non-empty disjoint open sets in capital X, such that capital X can be written their union, which means X can be written union of two sets f inverse of a, f inverse of b, such that they are disjoint, they are non-empty, they are open, which implies X is disconnected, X is not connected, but which is a contradiction, but because our assumption is X is connected. So why do you arrive some contradiction, some absurd result? Because we assume that y, if possible, y is not connected. So when you assume y is not connected, we get x is not connected. Therefore, which implies our assumption is wrong. That means y is connected. Y will be connected. So I can say that continuous image of connected set is connected, or connectedness is preserved under continuity, or f from x to y is continuous surjection if x is connected and y is also connected. Now we move to another property of connectedness. So let X2 be a topological space. Suppose we have a topological space X2. Okay. Now you consider the connected sets, some C1, C2, C3, etc. They are connected sets, collection of connected sets. Okay. Let script is equal to collection of C1, C2, etc. means connected subsets of X. Okay. And you are considering these connected sets such that they have no intersection elements, or I can say that no two members are mutually separated. No two members are mutually separated. That means, C1 and C2 are mutually separated means they have no common elements. Therefore, they must be disjoint to each other. Mutually separated are mutually disjoints. So, C1, C2, C3, etc. all sets C's are mutually separated connected subsets of capital X. Okay. Then we need to prove that their union then we need to prove that their union is connected. Is it possible? No. Because when C1 and C2 are completely mutually separated, they have no common elements, there is a gap between them. Okay, then how can we say that their union is connected? Suppose C1 and C2 are mutually separated sets, then C1 union C2 cannot be a connected set, right? ഒരിക്കലും കണക്റ്റഡ് ആവാനായിട്ട് കഴിയില്ല. അപ്പോൾ രണ്ട് മ്യൂച്വലി സെപ്പറേറ്റഡ് ആയിട്ടുള്ള സെറ്റുകളുടെ യൂണിയൻ ഒരിക്കലും കണക്റ്റഡ് ആവാനായിട്ട് കഴിയില്ല. അതുകൊണ്ട് അങ്ങനെയുള്ള സെറ്റ്സുകൾ എടുത്തു കഴിഞ്ഞാൽ അവരുടെ യൂണിയൻ കണക്റ്റഡ് ആണെന്ന് എനിക്ക് ഒരിക്കലും പറയാൻ കഴിയില്ല. സോ ദാറ്റ് ദേ മസ്റ്റ് ബി അറ്റ്ലീസ്റ്റ് വൺ എലമെൻറ്റ് കോമൺ. അപ്പോൾ അവരാരും തന്നെ മ്യൂച്വലി സെപ്പറേറ്റഡ് സെറ്റ്സ് അല്ല. Okay, we are assuming C1 and C2, C3, C4, etc. are connected subsets of X such that no two members of this collection are mutually separated. That means they are not mutually separated. They have some connection. They are not mutually separated. Then we need to prove that their union is also connected. Union C belongs to C is also connected. That means suppose we have some number of connected subsets which are not mutually separated, then their union is connected. Okay, so how will you prove this theorem? Okay, so I take let M is equal to union, this union is taken as M, union C belongs to script C. Script C consists of collection which is has elements which are connected sets and no two members are mutually separated. Okay, we need to prove that M is connected, right? So I assume M is not connected. Suppose that M is not connected. Then we will arrive at a contradiction. Okay, M is not connected. When M is not connected, I can write M is equal to some A union B, comma, where A and B are non-empty, disjoint, open sets or closed sets. I take closed sets here, closed sets in M. So since M is not connected, it can be written as some mutually disjoint closed sets, union of two mutually disjoint closed sets. Okay, when they are mutually disjoint closed sets in M, we have a result that if A and B are mutually separated, they are mutually if and only if A and B are mutually disjoint closed sets. So by that result, since they are mutually disjoint closed sets, A and B are separated. Okay, now you consider the collection C. It consists of connected sets, right? Then for every C belongs to C, when you take any C belongs to C, they are connected, C is connected, right? Connected. Therefore, and capital M is nothing but union of such elements. Therefore, for every C in C, that C will be belongs to M, because it is nothing but union. Every element will belongs to its union, right? So which implies C belongs to M means what is M? A union B. C belongs to A union B. What is C? Connected set. So a connected set is contained in union of two sets. A connected set C is contained in union of two mutually disjoint sets. Suppose this 8 figure is our A union B. So our C is a connected set which is contained in A union B. A and B are mutually disjoint closed sets. So by previous theorem, or I can say that C will be contained in either A or B. Okay, which implies C will be contained in either A or C belongs to, actually C will be contained in A or C will be contained in B by connectedness of C. Okay, so for every element in C, it will have this property. So I take some C alpha 1. Let C alpha 1 is an element belongs to or contained in A, and C alpha 2 is another element which is contained in B. Okay, for some alpha 1 and alpha 2 belongs to some indexed set, right? Okay, so which implies C alpha belongs to A and C alpha 2 belongs to B, which implies C alpha 1 and C alpha 2 are separated. Why they are separated? Because they are belongs to some disjoint sets A and B. Therefore, one is belongs to A and one other is belongs to 2 means clearly they are mutually separated sets. This is possible since A and B are separated sets. Okay, therefore C alpha 1 and C alpha 2 are separated, which means C alpha 1 and C alpha 2 are mutually separated sets, right? Is it possible? No. Because what is C alpha 1 C alpha 2? These are two elements in this collection C. What is this collection? This collection consists of connected sets such that no two members of C are mutually separated. Now we get two elements C alpha and C alpha 2 belongs to collection C such that they are connected and they are mutually separated. But it is not possible. It is not possible. Which implies what will happen? All C alpha belongs to C will be contained in either belongs to A or not belongs to B, right? All C alpha belongs to C alpha will be belongs to A or C alphas are belongs to B. This is the only possibility. That means the collection C consisting of elements C such that they are always belongs to either in A or in B, which implies their union C in script C will be contained in either in A or in this union C will be contained in B, right? So which means this collection is either contained in A or this collection either contained in B means either A or B must be empty. Which implies either A or B must be empty. But it is also not possible because A and B are which is also is not possible because A is the separation. Since A is separation, they can't be non-empty. So they must be non-empty. They can't be empty. Okay. So that means M will not have such kind of separation. That means M must be connected, which implies M is connected. Okay. Now consider the corollary of the previous theorem. Let C be the collection of connected subsets of a space X. And suppose K is a connected subset of X such that C intersection K is not equal to empty for every C in C. Then union U in C union K is connected. That means suppose we have a topological space X2. Then you consider some collection C such that they are connected subsets. Some connected subsets in C. Okay. Now K is a set such that which is intersecting with every element in this collection. Suppose K is a set such that which is intersecting with all these C's. This is our K. Then this is intersecting with all the C's. Suppose this is C1, C2, etc. Then K intersection C1 is non-empty, K intersection C2 is non-empty, etc. Therefore, I can say that their union C, all these C's, union K is still connected. Yes, it will be clearly connected by the picture, right? So, how will you prove this corollary? So, we have to use the theorem. So, for that, let D equal to, I take a new set D equal to union C in script C, okay, union K. What is our claim? D is connected. This is we need to prove. Okay. Since if we choose D equal to this can be written, then D equal to union C in C union K. This can be written like this. Okay. Now, since C intersection K equal to empty for every not equal to empty for every C in this collection C, I can say that C union, which implies C union K will be connected for every C in C, right? രണ്ട് സെറ്റുകൾ തമ്മിൽ ഇൻ്റർസെക്ഷൻ ഉണ്ട് എങ്കിൽ തീർച്ചയായിട്ടും അവരുടെ യൂണിയൻ എന്തായിരിക്കും? കണക്റ്റഡ് ആയിരിക്കും. ഓക്കെ, C union K will be connected for every C in C. And the previous theorem says that when you have collection of connected sets such that no two members are mutually separated, then their union is connected. Here, if you consider C union K as a one set, then if you are varying C in script C, C union K, it will be collection of connected subsets, right? Then consider the collection of C union K such that C varying over C. It is a collection of connected sets, because each C union K is connected set, right? It is a collection of connected sets in X such that if you consider some C1 union K and C2 union K in this collection, then what is their intersection? C1 union K intersection C2 union, if you take two elements in this collection, then what is their intersection? That intersection is C1 intersection C2 union K. And what is C1 intersection C2 union K? This K is always intersecting with, we have K has the property that K is intersecting with the every elements, right? So, and or I can then C1 union K closure A closure intersection B. Okay, so C1 union K closure intersection C2 union K will always contains C1 union K intersection some C2 union K, and which is clearly non-empty, right? So which implies if you consider any C1 union K and C2 union K, C1 and C2 are arbitrary, then first set closure intersection second set is non-empty. Similarly, you can prove that C1 union K intersection C2 union K whole closure is also non-empty, and this is true for every C1 C2 in C. So which means every Ci union K and Cj union K are not mutually separated, right? Which implies Ci union, I take Ci union K and Cj union K are not mutually separated in collection of all C union K such that C in C, and for every I and J. So which means this collection has all the properties of the previous theorem. Therefore, by that theorem, their union will be connected. So by previous theorem, union C union K, C varying over C is connected. And what is this? This is nothing but union C in C, C union K is connected, and this is D. So, using this corollary, I can prove one more interesting theorem, which is product of connected space is connected. So, next proposition. Let x1 and x2 are be connected sets to connected spaces. Then x is equal to x1 cross x2. You would consider x equal to x1 cross x2, which is a product space of x1 and x2. Okay, and the topology on x is nothing but product topology. Then x equal to x1 cross x2 with the product topology is connected. So that means if x1 and x2 are two connected space, then their Cartesian product is again a product topological space with the product topology, then which is also connected. Okay, so how will you prove this? If x1 equal to empty or x2 equal to empty, any of these sets are empty, then x1 cross x2 will be clearly empty. Empty cross x2 or x2 cross x1 cross empty or empty cross empty, that all are become empty sets. So nothing to prove. Then we have nothing to prove. So assume x1 and x2 are non-empty. Okay, that means they have elements. So now I take an element, let x1 belongs to capital X1 be fixed. Okay, then you consider singleton x1, this element as a singleton set cross x2. Okay, then this set will be actually homeomorphic to x2, because since x1 is a fixed element, then actually the elements are of the form some x1 comma any y where y belongs to x2, right? ഇതിനകത്തുള്ള എലമെൻറ്റ്സ് എങ്ങനെയായിരിക്കും? എലമെൻറ്റ്സ് ഇൻ ദിസ് സെറ്റ് വിൽ ബി ഓഫ് ദ ഫോം സം x1 comma y where y belongs to x2. These are the actually elements in singleton x1 cross x2, right? Okay, then if you consider a mapping from f from singleton cross x1 to cross x2 to x2 as f maps f of xy equal to x1 comma y. x1 is a fixed element, so x1 comma y as y, then this map will be biject to y continuous. Therefore it is a homeomorphism. So these two sets are homeomorphic. Ready? And since we have assumed that x2 is a connected set, okay, we have assumed that x2 is a connected set. When two sets are homeomorphic and any one of them is connected, then another one will be also connected, because homeomorphism, connectedness is actually invariant under homeomorphism. Connectedness property is invariant under homeomorphism. Since connectedness is invariant under homeomorphism, ഒന്നിനുണ്ടെങ്കിൽ മറ്റൊന്നിനുണ്ടാവണം, എന്നാലേ ഇവർ ഹോമിയോമോർഫിക് ആവുള്ളൂ. Homeomorphism and x2 is connected implies the set x1 cross x2 is connected. Okay, and this is nothing but singleton set x1 cross x2 is connected. In a similarly, I can prove that for a fixed x2 belongs to x2, x1 cross singleton set x2 will be homeomorphic to x1. Okay, and since x1 is connected, which is also connected, right, implies x1 cross the set x2 is connected, right, in a similar way. Now what will be their intersection x1 cross x2? This is the first set, intersection some fixed element x1 cross x2. These two are sets which are subsets of capital X, right? Okay, what about their intersection? And these are two actually connected sets. So x1 cross singleton x2 and singleton x1 cross x2 are two connected subsets of capital X. Okay, now what is their intersection? Can you assume any one element which is common to these two sets? So I can say that which is always non-empty, because since x1 is fixed and x2 is a fixed, then the pair x1 x2 is an element. Since x1 belongs to capital X1 and x2 belongs to capital X2, the ordered pair x1 x2 will surely belongs to x1 cross x2, and it is also belongs to x1 comma x2 is also belongs to singleton x1 cross x2, and it is also belongs to capital X1 cross singleton x2. അല്ലേ, ബിക്കോസ് x1 ഫിക്സ് ചെയ്ത് കഴിഞ്ഞ് കഴിഞ്ഞാൽ x1 ഇവിടെ ഉണ്ട് എന്ന് ഉറപ്പാണ്, അതാണ് ഫിക്സ്ഡ് എലമെൻറ്റ്. x2 വേരി ചെയ്തോട്ടെ, പക്ഷേ ക്യാപിറ്റൽ x2 വേരി ചെയ്യുന്നത് കൊണ്ട് തീർച്ചയായിട്ടും ഈ പെയർ ഇവിടെ ഉണ്ടാവും. ഇനി x2 ആണ് നിങ്ങൾ ഫിക്സ് ചെയ്തിരിക്കുന്നത്. രണ്ടും ഫിക്സ്ഡ് എലമെൻ്റ് ആണ്. സിൻസ് x2 is fixed element, x2 will be belongs to here, right? And x1 is a varying element, therefore x1 belongs to capital X1, right? Therefore this ordered pair will always belongs to this one and this one. That means their intersection. So this x1 x2 fixed elements x1 and x2 form an ordered pair x1 x2 that will surely belongs to their intersection. Therefore this intersection is non-empty. So this, suppose you consider it as a C1 and this is some C2, then C1 and C2 are two connected subsets of a topological space X such that they are not mutually separated. Their intersection is non-empty means they can't be mutually separated. Okay, so C1 and C2 are not mutually separated, which are connected subsets of capital X. Therefore we can say that their union will be connected, right? Which implies x1 cross x2 union x1 cross x2 is connected. When two sets are not mutually separated and they are connected implies their union will be connected. So by that result their union will be connected subset of X, product space X. Okay. But we want to prove that whole x1 cross x2 is connected, the whole space. But we have to prove that x1 cross x2 is connected, right? Product of two topological space connected spaces are connected. But now we proved that x1 cross singleton x2 union x1 cross capital X2 is connected. Okay. Now you consider union of all x2 varying over capital X2 x1 cross singleton x2 union. Okay, what about this set? Actually, which union x1 cross x2? Okay, consider this union. Is it connected? Yes, because by previous theorem, when you consider this as some k, okay, and these are some c's, okay, and actually, yeah, then we have a corollary that we proved a corollary that when C is a collection of connected subsets of a space X and K is a connected subset of X such that C intersection K not equal to empty for every C in C, then this union will be connected. Okay, so by using this corollary here I can say that, consider this is our K, these are C's, and C intersection K will be clearly non-empty because x1 x2 is a member belongs to their intersections, right? So this K will intersect with all these C's. Therefore by that corollary their union is connected by previous corollary. We have to mention that corollary in the proof of this theorem, okay, proposition. Okay, so this will be connected by previous corollary. And what is this actually? This union is nothing but you are varying x2 here, okay, then you take unions of x1s, okay, then what will be this actually? It is nothing but x1 cross x2. So which implies x1 cross x2 is connected. Okay, thank you.